We continue with our book TensorFlow 2.0 Computer Fusion code book, and we're looking at chapter 1. The last time we kickstart running of the different models, and we see how we can do an assemble model and do the average of the models if you need to do average of different models of the same models run multiple times. So we'll continue now. We still want to explore how we can load images using the Keras API, and we already have Pillow installed thanks to Google Colab for that. So we import the necessary packages, and here they use the Scenic 10 dataset, but we are having an issue importing the Scenic 10 dataset. So as a result, I'm using package from the Google API, which is the flower photo instead of that. So we can run that. I think the file extension should be tgz. So tgz. Have the file extension here. So we can run this and run this. And so we have the dataset name is should be, this one is flowers. So this is flower dataset, flower underscore photos underscore photo. Alright, so we have that running, and the photo as S. Sorry. Okay, so we can now get the file with this code, the download file. So that downloads the file, and I can delete all this other one, this other code. Okay, so we have that downloaded already. In the get file. Then we build the path to the data directory based on the location of the downloaded file. So that's what this code is doing. So we build a path, and we can extract our GZ. I hope we'll be able to extract the GZ using that. Let's see. That works well. I was expecting that, since we are using tgz, not tar.gz. Okay. Then we load all the image. These are pretty straightforward. We build a path to the directory, data directory. Then we load all image path and print the number of images. So let's see that. So that's what this is doing. Now our photos is not a PNG, it's a JPEG. So it's a JPEG. So we need to modify that here. So this is a JPEG. So this is the JPG. We can modify that and see what we have in the file. And then further, the data set. There's 0 images in the data set. What could be wrong? I guess this didn't extract the GZ file. So what else could we have used to extract? Instead of using the tab file, So we import TAL file. Okay, there be GZ file. So let's see, there's the GZ file, TGZ, to use to extract that. Okay, so let's use another method instead of going to what they used here, since we're doing something slightly different. So let's use a separate method from the TensorFlow API. So I'm copying this from the TensorFlow tutorial. So this is how this is implemented in TensorFlow. So they use this. They use the get file tool, and they use the path lib. And after downloading, we can easily get all the images into image count. So we can get the images into image count. So those are the number of images. We can use pillow to see all the roses in the images. So this is pillow library. So we have our data directory. We use the glob to grab all those that start with that are in the folder roses. We put it in roses, and we can use the pillow to image to open it, and we can display the first one. So we've not import PO. So let's import PO here. We're supposed to do that early, but we can do it here too. So let's just import PO here. So import PO, and that displays the rows that we have. Okay, so we have the rows beautifully displayed there. We could see some more. Let's see the last item. Yeah, that's the last item. Let's see the second one. Yeah, that's interesting. Okay, so we have that roses. All right. So now that we now have this for roses. So this gives us all the roses. The next thing here is load a single image from the dataset and print it metadata. So let's see how we can harmonize the code here now. So we want to load a single image from the dataset. So this is the sample image. So let's see this sample image. Now some things will have changed. Now we're using the load image. The load image, this function is coming from what we already import. We import the load image, so we import it from Keras, the pre-processing image. So we use that to load image, and it takes the image path. So in our own case, we don't have we had the data directory. So essentially this is what we'll be loading. Let's see, roses. So I don't know what they, if we are loading a rows. Okay, that works. And let's see where we're now printing out the type of the sample image and information about it. So we can now see that that works quite well. So it's giving us information about it. In this case, the image format is PNG. In our case, that's a JPEG. The mode is RGB, and the size is 500, but the width and the height is 313. All right, good enough. All right, so we can proceed on and convert an image to a Numpy array. Remember, we're just doing some processing. So to convert to a Numpy array, we take our sample image and we use the image to array. Don't forget, the image to array was imported from the keras that preprocessing here. So this is the function we're using. So we're taking the image and we are converting it to an array. So using this, and this will be the sample image, that is the array format. See the naming convention. Then we can print the type of that, and we can print the shape as well. So let's run this code and see the sample image when it is converted into an ND. So you can see the type now is an Numpy n-dimensional array, and we can use the shape attribute to get the shape that this is the width, this is the height, and this is the color channel, which is 3. Okay, so we can use matplotlib to display an image. So we have already imported the matplotlib. We're just demonstrating that, so we can use the matplotlib to display the image. You can see that we actually normalized it before displaying. So okay, we can load a batch of the image using the image data generator. So that we want to load it into batches for training. So, and at the same time, we rescale each image to the range 0 to 1. These are standard practices when you are processing image in machine learning. You need to rescale the image, and you need to ensure that they are normalized. So we do a batch processing of that. So let's see that here. So yeah, we are using the image data generator. So the image data generator is taken in, it's going to creating an object of it. We'll rescale, then we also flip. All right, and we use the image generator. We pick and display a random batch of 10 images directly from the directory. Okay, so we have this image generator, specify the directory, the batch size is 10, then we now iterate through the iterator, and we want 5, 25, 5 by 5, and we can plot that. The figure size is 5, sorry, so we can plot 5, that is 10. Okay, so these are pretty standard, so let's run this. Okay, so we need to check, do we have the data directory? So we see that, do we have the data directory? The data directory. So we have the data directory here. So it's got data underscore dir. So we can just come in here and say data underscore dir here, and we can plug that. Yeah, right, pretty interesting. So we have 3670 images belonging to 5 classes, and we're able to print 5 of them. Yeah, these are pretty standard. So you create an iterator, you flow from the data directory. This is the batch size. So in that batch is 10 because we have said we are looping through one batch. So in that one batch we have just 10 of it. Okay, then we can use the PL to show do that. Next, it's loading images using the tf.data.dataset. So that's another way we can load the image. It's pretty straightforward like we did before, so I will not go over this one because we're not even using this directory. I have problem downloading that. You go through the download process as well. You've gone through extraction, you've joined in, then where the difference is now here, where you use the tf.data.dataset list file data pattern. And you can take a single part from the data and use it to read the corresponding image. So just take one, convert to Numpy, then we must convert it into a format a neural network can work with. So you decode it in a Numpy, so decode PNG, specify the channel, and display the image in Matplotlib. Okay, you can take the first element, 10 elements from the image data set, decode, normalize, and display, just like we have here. Okay, so how do we save and load a model? Let's see that. So we train a CNN on a MNIST data set, and this is also pretty straightforward. We have already trained a model before, so I'll just jump to the part that where the saving is done. But we'll walk through this. Is importing the necessary libraries, necessary packages. Then we define a function to be able to do the normalization of the train and test, and you reshape this. This is always necessary because you are dealing with a grayscale image, because you are going to be using MNIST like they said. So you need to include this code where you use the pattern expand dimension and to give it the axis 3. So this is very critical because our convolutional neural network assumes that it must be because the third channel is not there, it's not specified as 1. The X train normally just specify it as just 28 by 28, but when you put this, it puts the 1 in the 28 by 28 by 1. Maybe we should see that so that I'll quickly run that for us to be able to see why we need to expand since we're training a CNN. The first tutorial that we went through, since we were training we're not using CNN, we're using dense layer, we didn't have to do that. So let's see this just for learning purpose so that we can get what we mean. Okay, now so we define this function here, we do the reshape. I'm going to edit that so that we see what I mean. So this is the function. Now I'm going to print the shape of X. So print the shape of X before the X train shape before expand dimension. So So we want us to see that. So I can say x underscore train dot shape. Then let's see it again after we expand it. So this is after we have expanded it here. Let's see the extension after we have expanded it. Okay, so we run this. What is the problem there? Indentation. So this should go inside here. We're having indentation error. So let's try and see what's going on. Okay. Okay. So we can move all of them backward and see what that gives us. Great, so that works. So now I want you to see if I call this function load data. So you see the load data function. We call the function now. Yeah, it downloads that, and you can see that it actually here. Let's see the beginning of that. Yeah, you could see here. This is what I'm trying to say. This is before we use the expanding. You see that this one is not there. Now that we have used the expanding, so it now creates that extra component. It needs to specify how many channel. So in this case, one channel. This is the number of samples in the training. This is the width. This is the height. But CNN requires that we expand that and have additional value here, so making 4 component in our tuple to specify how many channel, which is 1 in this case. Okay, so that's the reason why I did that, for us to see. So let's now define a function for building a network. So the architecture comprises a single convolutional layer and 2 fully connected. So we've already seen this before, so we'll move fast. So here we're using the functional style. We use the input, we declare the shape, and we define our convolutional layer. It takes the kernel 2 by 2, the padding is same, the stride is 2 by 2, and the number of filters is 32. So these are pretty standards that we should know already. Then that takes in the input layer as functional. Then we define ReLU, and we take this into a ReLU, then activation, and we take this into a batch normalization, and batch normalization comes in here. Then we define our pooling, the pool side, the stride, and dropout takes the pooling, the rate, then the flatten layer takes the dropout flatten, then the dense takes the flatten, the number of unit, the dense is 128. Then we use ReLU, so this one activation takes and this, then final is the final layer has 10 unit, and we put the source mark over this because we are having multiple multi-class classification. Then we define our network with model input. Normally they use input equals input, output equals output. Then we return our model, or which is also called our network. Okay, so let's see that. So we're defining fully convolutional a CNN, a convolutional neural network here. Yeah, we have issues of space in here, so this should be on the same line. here, this one, and this padding, it should come up here. This is dropout, flatten, division, pulling, then we return the network. Yeah, so that works. Let me see whether we're able to use the network as a summary. Get a summary of the network. Yeah. It's not yet defined. We need to call the function, sorry, build network. So build network, return network, and we can get a summary from here. Yeah, so that works. So we get our network. You can see the layers that we defined. So the output, I'm just worried why you have output shape here, because you have the input shape is 20. Okay, let's say the first layer, the first layer is the input. Okay, so the output of input layer is 28 by 28 by 1. The none is the batch size, which we don't know yet. Then the output of the count, because this strides of 2 by 2 is going to reduce this by half. It reduces this by half. Then ReLU, there's no parameter to learn in ReLU, so it stays the same. And something important you should see here, the number of filters is 32 specified in comp2D. You will see that what we specify as 32 is the number of filters here. So anytime any number of filters that we specify, that will now become like in replacement of the channel. So instead of saying channel 1 for grayscale or channel 3 for color RGB, now the number of filters now essentially replaces the channel, so there are 32 filters. Then batch normalization, nothing happened in the batch normalization. Then the next thing we defined is the max pool 2D, nothing happens in max pool 2D, there are no parameters to learn. And you see that the size is actually the same in max pool 2D because our stride is 1 by 1. If we have specified 2 by 2 here, that will have reduced the size. Okay, and if you try it, you will see what I mean by that. So let's use our max pool 2D. The strides is actually what reduces the size. So if we put 2 by 2 here, now by the time we define our network here, we should have 7 by 7 here. It should have become 7 by 7. You see what I said? So the stride changes that. Okay, so that's just for defining our network and the effect of using the strides on our network. Okay, so it comes back to 14 by 14 like we have before. So we have the dropout, nothing happened dropout. We flatten. Essentially flatten means that what the flatten layer does is that it just takes all these 3 components and turn them to 1. We see how the batch side. So if you multiply 14 by 14 by 32, you are going to get that values, and you can see the 14 by 14 by 32. You will see what we have. So you have 6272. That's what the flatten does. Okay, so because essentially our image, it's our image, it's like a box. So our image is like a box. So just like we display the image here, so it's a box. It's a multi-dimensional array. So it's a matrix. And when we flatten it, it becomes a list. Yeah, it's become a single channel array. So that's what the flatten does. Then we pass it through the dense. Notice again that the number of units we specify in the dense is what we eventually have as the output. So from 6272 we have 128. So it turns to 128. And from 128 we have 10. So whatever value we put there is 10. And the softmax layer does not do anything, just try to create a probability distribution over the 10 classes and make sure that they sum up to 1. Okay, the next is a function that we evaluate a network using the test set. So we implement a function that we evaluate a network, and we can see here. So this is a function. So this is pretty standard. So this is a function. So we can use this function, takes a model and it evaluate. We put in the text and the white test and it evaluate that. It also gives this is for the loss, but we are interested in accuracy. So we prepare the data now and we split it. We get the validation from it. So we use 80%. This is 0.8. Means we use 80% for training and 20% for validation. I'm sure we all know the importance of validation, so we know how our network is doing on same data during training. Okay, and the next thing, it's we can compile. These are pretty standard. We choose 50 epochs as an hyperparameters that we choose, and we choose a batch size of 1024. You can experiment with different batch sizes, but it's normally a multiple of 2. So like 512, 256, 32, 16, 0 about 64. So we compile with this. We use categorical cross entropy, matrix accuracy. Said this before. We specify a batch size, the number of epoch, the validation data. So these are pretty standard, and verbose help us to be able to display the information as it is being trained. So that is so if we say verbose equals to 1, we expect that information will be displayed as this is being trained. So I really like to see that. Let me interrupt the runtime and set the verbose to be equals to 1. I think 1 actually makes sure that it's displaying, so you could see that. So 1 shows us how that it is training and it is displaying. Let me see if we're using GPU. Or we're not using GPU, so let's use GPU. That's going to disturb our stuff, so we just leave it because it will restart our runtime. So that will run. So while that is running, let's continue to see the other ones. We just interrupt this and save it for a smaller number of epochs, since our reason is so that we experiment. So let me just save it for 5. Let me just run it for 5 epochs. Okay, so now how do we save the model? To save the model along with its weight in HDF5 format, there are different ways you could save a model. So one of the ways to save it in HDF5 format, we use the save method. Then you can load the persisted model using the load method and use it to evaluate the network performance on test set. So this is going to save our model as a file on our disk. So this is what you do. You call the model name and use the save, and you give it the name that you want to use to save it. Pretty simple. And to load it back, you use the load model. You discover that this the load model we have imported, but the save method comes with the model itself. You see that this load model we imported it. So let's see the load model again up there. It should be far away up. Now, where did you get the load model from? No, I'm wrong there. We didn't get it from. Let me see where we get the load model. Load model. Well, I can't remember where we get this from. Let me see where we get this from. Control L, load model. Okay, then load the persisted model using the load model and evaluate. Okay, but where did you get that function from? Okay, so because this model is still uh, it's still a memory. I guess that's why we can still use the load. Aha, I said we imported this from somewhere. Yeah, this is it. So this is it. We load it from TensorFlow dot keras dot model, so we can use this to load the model. That's where we loaded. We get that function of loading model. So let's save the model now. So to save our model, we can use this to save the model. And if you come in here, you will see that the model has been saved here. So that's the model, that's the name we gave it to. Then we can, since we have the model there, we can use this to load the model again. And I normally call this new model. So let's say model new. So this is a new model. Let's see the verbose one. So we could display some things to it. Loaded model is not defined. Oh, sorry. This is what we're doing. This one. This is what we should do. We need to have this. What we're doing there is we're doing inferencing. So sorry about that. So this is load model, and we load the model into model new. Then we can use the model new to do evaluation on the test data. So even if we restart the state of this, once we have this file uploaded here, we can just use this function to load the model, and we can use the name of the model that was just loaded and just run that. So we have a test data set that's not defined, so we didn't define our test data set. So let's see where our test data set is that we did not define that. Oh, so we have test data set here we didn't define. I thought we define our test data set. Okay, so it should be x test. It should be x test. Is that not? So we can run it on x test, right? So it should be x test. It's a bit different from what we were doing before. I think we have mixed things up there. We have moved far away from where we were before. Let's go back. So this is where we were. This is what we defined. This is what we ran. So model summary. Okay, I think we have jumped too far. We have jumped too far. So we have jumped too far. So let's go back. Let's retrace our steps. Okay, this is where we were. Good. Yeah, so this is where we're supposed to be. So this is where we save the model. Now we load the model back. Then we can predict using the loaded. So this is the x test. So this is what we're doing. We have moved to another one. So this is what we need. So we just evaluate, but we have changed the name of our model to model underscore new. So we put model underscore new here. Now we can now see the evaluation of our model. This is not supposed to be. Sorry about that. So just see our accuracy. So this 96%. Even with 5 epochs, we already have 96%. That's awesome. Okay, so that's that for the continuation of our chapter 1. The next time we will still continue with how to visualize our model, and we will see how we use Pillow Pi dot to visualize our model. Thank you very much for listening, and see you in the next one.